My name is Sumudu Tennakoon. This is my project for Machine Learning Foundations for Product Managers course under AI Project Management Specialization offered by Duke University. In this project, we are predicting electrical energy output of a combined cycle power plant. The dataset given by the course creators had about 9,568 hourly records of ambient environmental conditions collected from power plant sensors. This rating served as a predictive features for our modeling process. Other variables provided are temperature, ambient pressure, relative humidity, exhaust vacuum. First I did was I loaded the dataset into a pandas data frame, and then I did some exercise to go through the exploratory data analysis work to get to know the data set a little better in terms of the descriptive statistics and data types and correlation coefficient. And also I worked on getting the pair plot using the pan as the seaborn library to know the data distribution, how visually looks like. So there I could get to know about some relationship between the the variables itself with each other. And then I did like some identification of the distribution using another data visualization technique, box plot, and found out like there are some potential outliers present in some variables, but I would not that concern in this course project. In the modeling approach, so this exercise, we are going to predict a continuous variable using another four different continuous variables as features. So therefore, I choose this problem solution as a regression type of a solution. I chose three different models: linear regression, elastic net regression, and random forest regression as my model candidates. I also used tree regressor, decision tree regressor, as another comparison for random forest regression, but I'm not going to consider that as a candidate for the final selection. The model evaluation, I'm going to use the mean squared error and the R square or R2 score. So with identified features, I first did some data pre-processing, assuming like we are going to the regression models, and then we need to have a scaled models to have the best performance of the model. So I used the standard scaler from scikit-learn, and then the most importantly, the data set. We wanted to make it split into train and test samples. So the train data set I'm going to use to train the model, and test data set I'm going to evaluate the model performance after the training is done. The next item is like we wanted to make the first model, just an attempt like I built the linear model in scikit-learn library. So you use the linear regression just as a first model and get a trial model using the features and the target variable. And also I use the evaluation metrics to find out how good the model is. So I got like about 21.2 mean square error and then 90.927 as the R square value. And then I built a small function to replicate the model building exercise for the linear models, and where you can pass any linear model and with the training data set, your testing data set, and the set of features and the target variable. So using that, I first did the linear regression model. I fit the linear regression model and find out the model coefficients, variable coefficients, and the intercept, and also get the model evaluation, the mean square error, and R2 square. Then I repeated the same thing with the elastic net regression. So in the elastic net regression, I did the same, get the model parameter coefficients, and then the intercept value, and then did the evaluation. I did not notice the like a significant difference between two linear models I choose. And then I repeat the exercise with the scaled variables. Previously, I applied the raw variables without any scaling, and then I had the scaled variables I have done before. And then I applied the same for the both models. Here also, I did not see much difference, except the elastic net regression got performance got a little degraded with the scale variables, and they didn't see any improvement with the scale variable in this one. So I may need to do more work on the variable data preparation if I wanted to get more success on that one. Then I went to the decision tree model. So in the decision tree model, I just initially created a function similar as to the linear model function I created above. And then using the same function, I used the decision tree regressor with some parameters I choose, the max depth, mean sample split, and mean sample sleeve. And I got like a decent model, but it's not the best model you could think of. But I got the model evaluation parameters, like mean square error is 27 and the R square value is 90%. And also as a tree based model, I could get the feature importance. One of the significant thing I can highlight here in the feature importance is the temperature plays a crucial role in the model prediction, and it is about 96% or 97% importance from the tree regression. Then I also did that visualization of the decision. So you can also take a look at this notebook in my GitHub repo. And then I went to the random forest classifier, try to build a model with the different settings. Means like different hyperparameters, number of estimators, max depth, and find out like the model is getting better with the number of estimators are high and the max depth is getting a little higher. So then I went to the evaluation with cross validation, just as a kind of attempt to visualize like how the evaluation looks like. I just did the kind of cross validation with five-fold cross validation, and found out like it's reasonably okay with of the mean square error for all across the different faults. And something to note here, so in the cross validation, we use the negative mean square error as the function provided from the scikit-learn library. The reason is higher the value is the better in this the cross validation score. So therefore, we wanted to make it the negative cross validation, because higher the mean square error is, the worse the model is getting. Okay. And the mean square error for this more final model, I got about 18.1, and the R2 square is about 0.9338. So then I went to the model building again with searching a best set of hyperparameters with the grid search. So I applied the grid search method for both elastic net regression and the random forest regression. And then for elastic net regression, I have in the notebook with the parameters I used, which is alpha, regularization strength, and then the L1 ratio, so which is the ratio between L1 and L2. And also I just used the max iteration just to play with that the number. And then I found out the best set of parameters is alpha is 0.01 and N1 ratio is about 0.25, and maximum iteration is 1000 for the elastic net regression. I got about 0.927 R square value, and the mean square error is 21.2. And then I did repeated the same grid search for random forest with its own parameters and estimators, max depth, min sample split, and minimum sample sleeve. And you have the description in my notebook. And then I found out for the random forest regressor, the max depth is 5, min samples per leaf is 5, and min samples per split is 5, and then n estimators is 50 out of the parameters I provided above. So this gave me the best the model, and the mean square error here was 18.1, and the R square value became 0.937. So you can find out the grid search results also here. And then I conclude out of the models, the random forest regressor is the model I'm going to use if I wanted to apply this model into a real world application. So the reasons are random forest model is less risky for the overfitting scenarios compared to the tree regression. And the linear regression is also good, but linear regression model is perform less than the random forest regressor with this best set of parameters. All right. Thank you for listening to the presentation, and I hope you can look at and get more information by reading through my notebook. Thank you.